Could a revolutionary new telescope finally solve astronomy's greatest modern mystery? While current searches for Planet 9 face significant limitations, a next-generation observatory scheduled to begin operations in late 2025 promises to transform our ability to detect distant solar system objects. The Vera C. Rubin Observatory, currently under construction in Chile, represents what many astronomers consider our best chance, yet to either confirm or refute the Planet 9 hypothesis. Astronomy has historically been transformed by new observational capabilities. Just as Galileo's telescope revealed Jupiter's moons and Hubble unveiled distant galaxies, a remarkable new observatory may soon resolve one of modern astronomy's most compelling mysteries. Located on Cerro Pachón in northern Chile, this facility offers ideal viewing conditions with clear skies, high altitude, and excellent access to the Southern Celestial Hemisphere, where much of Planet 9's predicted orbit likely resides. The Rubin Observatory represents a fundamental leap forward in our capacity to search for faint, slow-moving objects. Three revolutionary capabilities combine to create an observing system perfectly suited for finding objects exactly like the hypothesized Planet 9. First, its 8.4-meter primary mirror gathers substantial light from extremely distant objects. This meticulously polished mirror concentrates faint light, with its collecting area directly correlating with the ability to detect dim objects. Second, its 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy, captures images with extraordinary detail and sensitivity. This massive LSST camera can detect a golf ball from about 15 miles away and holds 40 full moons in a single exposure. The camera's focal plane contains 189 individual CCD sensors, creating an effective imaging area 40 times larger than the full moon. Third, the observatory employs an innovative observing strategy called the Legacy Survey of Space and Time, LSST. This approach systematically photographs the entire visible southern sky every few nights. Over its planned 10-year operational period, the telescope will visit each portion of the sky approximately 825 times. This repeated coverage creates a time-lapse of the night sky, allowing astronomers to identify objects that change position. Each image is stacked and compared with previous ones, making it possible to detect extremely faint objects invisible in single exposures. For the Planet 9 search, this strategy automatically identifies anything moving relative to background stars. The LSST survey will catalog an estimated 37 billion stars and galaxies. Among these, it will likely detect millions of solar system objects, including approximately 100,000 new trans-Neptunian objects. This expanded census will provide more evidence of Planet 9's gravitational influence and might directly image the planet itself. Scott Shepard, staff scientist at the Carnegie Institution for Science, whose work contributed to the Planet 9 hypothesis, has expressed remarkable confidence in the Rubin Observatory's capabilities. According to Shepard, the observatory has a 70 to 80% chance of finding Planet 9 if it exists. This high probability stems from the observatory's combination of sensitivity to faint objects and comprehensive sky coverage. For a cautious scientist like Shepard to suggest that such a high probability indicates real confidence in the observatory's capabilities. The observatory's software systems match its impressive hardware. Sophisticated algorithms will analyze the massive data stream, automatically flagging objects showing the telltale motion of distant solar system bodies. The system will generate approximately 10 million alerts per night for objects that change brightness or position, with specialized filters designed to identify the slow movement expected from a distant planet. This automated processing addresses one of the greatest challenges in the Planet 9 search, distinguishing a slowly moving planet from millions of background stars and galaxies. Processing about 20 terabytes of data nightly, the specialized software will identify the most promising candidates for follow-up observation. The Rubin Observatory will also help resolve whether the observed clustering of trans-Neptunian objects is statistically significant or results from observational bias. By systematically surveying the entire sky, rather than focusing on limited regions, the observatory will establish whether the apparent patterns in TNO orbits persist in a larger, more uniform sample. What will the Vera C. Rubin Observatory reveal about Planet 9 starting in 2025? It could finally confirm or rule out Planet 9's existence. If Planet 9 exists within the parameters scientists have calculated, the observatory has a strong chance of finding it during its 10-year survey mission. Equally important, if the observatory doesn't detect Planet 9, that absence would indicate that alternative explanations for the observed orbital clustering deserve more serious consideration. The fact that we're just a few years away from potentially resolving this major scientific question highlights how scientific progress often depends on technological advancement. The Planet 9 hypothesis emerged from careful analysis of existing data, but its confirmation requires new observational capabilities that are only now becoming available.